All right. So today we're going to talk about more turbulence. I started turbulence last Thursday, and I went real fast through all the important stuff. Um, Today I'm going to do that. I'm going to do all of that stuff even faster, but I'm going to do it again so that we see it again. Um, and then I'm going to talk about the nasty, needy stuff of the chapter. That it's like this long in the chapter. It's like about a page, maybe a page and a half, but it's very dense, and I'm going to spend most of the lecture on what really amounts to like 4 lines in the text, just because he's a little terse. So we're going to talk about correlation functions. We're going to talk about turbulent diffusion. I'm going to set up the turbulent cascade as well because it's a thing that we need. So this is a thing we're going to build in. Yeah. So, what is turbulence? Turbulence is random motions, random chaotic motion at high Reynolds number. There's probably more to it. If you ask people who study turbulence for a definition of turbulence, if you ask 4 people for a definition of turbulence, you'll get 11 answers because it's not really particularly well defined. It's when stuff gets all messy, but when it's turbulent and when it's merely random is not necessarily obvious. Turbulence means fully developed and fully chaotic. So what is it really? Why do I say high Reynolds number? Because if we remember Navier-Stokes, dv dt plus b dot grad v equals minus 1 over rho grad p. That's the fourth term. It's not very interesting. Plus nu del squared v. So the Reynolds number, remember, is LV over nu. And that is the ratio of this term to this term. So it's how much does this nonlinear bit impact things versus the linear bit, which is diffusive. So we talked on Tuesday about diffusion, just diffusion in general. And if I have d by dt of some quantity q equals del squared q, let's give it some coefficient d, this is an equation that we have the complete solution space characterized for. We know that it's always well behaved. If you put anything in here, it just smears it out. That's what this operator does. So this guy smears stuff out, and this guy makes stuff blow up. We saw this thing blow up when we did method of characteristics on Berger's equation. Berger's equation is when I throw these things out, and we're left with just this one. This one makes things blow up. So we have these two competing terms, one that causes velocities to get very large, and one that causes them to get smeared out and get smaller again. So what happens? Well, the first thing is, so we spent a bunch of time linearizing this equation, which means getting rid of this term and doing stuff. So a lot of times that works out great. A lot of times the linear equation is well characterized. Also, a linear equation, we have, again, the whole solution space characterized because I can just Fourier transform anything, and I know how these things look in Fourier space. When it's linear, I have that solution space characterized as well. But when it's nonlinear, things go south very quickly. So I can't show you any solutions of the whole equation when we have all of the terms important. So we have to wave our hands a lot because our math runs out. So couple things to think about. So we're going to assume for everything that we're doing, we're going to have homogeneous. That means the same everywhere. Isotropic. That means the same in every direction, and this one is super, super important. We'll use isotropy quite a lot when I'm talking in a minute. And incompressible. And incompressible, remember, means the density doesn't change. It also means div v is 0. So that gives us these two things. So what happens when I have So these are the first assumptions. The second assumptions is that we're fully developed turbulence. In steady state. So what this means is that, so the steady state means, so fully developed turbulence, I'll show you what this means in a minute. This means that we've got structures at all scales. Maybe I just 3 things. In steady state, so the steady state means that I'm not dumping energy into any particular part of the system. So say I've got a pool and I'm just kicking my feet in the pool, stirring stuff up. I'm dumping some energy into the system. That energy is getting dissipated by the fluid dissipation. So I have this steady state where I balance the input and the output in the energy term. Does that make sense? The result is that the system is random. It's as random as maybe as random as you can make it. So this is the setup. So I'm not going to do it all the way because I did it in the lecture that's online, and I'm going to make you do it for homework. But one thing that you can show is that d omega dt, remember omega is the vorticity and it's the curl of the velocity. D omega dt is omega dot grad v. And what this means is this is the derivative of velocity along a vortex line. So think about vorticity as like spaghetti. You've got these little tiny worms of spinning stuff. So along a vortex line, you'll have you'll have a velocity gradient from one point of the line to the other. That velocity gradient is usually positive because there are more ways to move apart than there are together. So this means that omega usually goes up, and by Kelvin's circulation theorem, omega times A is a constant. So that means that A usually goes down. That means things get smaller. So stuff tends to get to smaller scales when it gets fully turbulent because you get these little tiny bits of vorticity that you stretch out and they get smaller. Okay, this process is called vortex tube stretching. And I did this a little bit longer, more elaborate on Thursday, and I can answer questions if anybody's got any. But the basic tendency of a turbulent system is to make structures get smaller. So things get smaller. I'm going to write that over here. The upshots are things get smaller. How small can things get? Okay, we will come back to vortex tube stretching, especially in the homework. So the upshot is things get smaller. So how much smaller can something get? How much smaller can a little parcel of vorticity get? How much smaller can a little blob of fluid get? Well, we think about the Reynolds number. The Reynolds number is LV over nu. And when this is very large, then we're in the turbulent regime. But when it's small, we're in the dissipative regime. Because that diffusive term, that dissipative term, becomes important when this is like 1. So at some size scale, some LD and VD over nu, okay, nu doesn't change with scale, but if I think about small things, there's some velocity and length where this is equal to 1. So there's some small velocity and some small scale size, some small size structures And, well, we'll talk about what the velocity is. It's also small. Some small velocity structures such that dissipation wins. So we need to figure out what LD is. What's the dissipation length? We'll come back to that in a second because we need to figure out what how the velocity behaves with scale. Yeah.
Is there a specific point in which it swaps from turbulence and dissipation?
No, turbulence doesn't have nice phase changes like that. If there was a nice clean boundary, the whole thing would be a lot easier. But it's kind of goes from not really chaotic to kind of chaotic to a little chaotic to very chaotic, kind of smoothly. So I had this. I'm going to try to get this video for next time. I just sat at my dad's pool and I kicked my feet in the water, and you can see everything stir up, and you can see that turbulence decay, and it's really pretty neat to watch just the turbulence evolve. But it's never like, now it's not turbulent. So this, I'm going to write it down like it were a phase change, but it's not. So there's a lot of hand waving and squishiness. Okay, so I'm going to start by dumping energy in at the large scale. That's usually where things happen. Storms are much bigger than waves. Your spoon is a lot bigger than a little lump of cream in your coffee. So we dump our energy in at some large scale. So if we think about this, I'm going to think about this in Fourier space. So this is inverse length. So big stuff is over here. We're going to call this the injection scale. And small stuff is over here. We're going to call this the dissipation scale. So I dump energy in at the injection scale, and then things get smaller until the dissipation scale, and then it stops. And this is in log. So what am I drawing? This is the log of the energy, and this is the log of K. Why am I making them both log? This is a dumb cartoon plot. I didn't even put units on it. Because in a log plot, a power law is a line. So if I have a function that looks like E equals K to some alpha A, then the log of E is just A times the log of K. So this is a line, right? There's a plus B over here if you want. So this is just A times M times X plus a constant if you did it that way. So in a log-log plot, power laws are lines, and this becomes a power law. And I'll show you why. So the energy, so where does the energy go? If I'm sitting right here, I'm in the inertial range. So we call this part the injection scale. Oh, I wrote that down here. This part is the dissipation scale. This in the middle is called the inertial range. And it's where the inertia term is dominant. So this part is where this one is dominant over this one. So now in here, where does the energy go? It doesn't get dissipated because this term does the dissipation. Energy leaves the system because of the diffusive term. Energy stays in the system, so it just goes from one size scale to another size scale. It just gets smaller. So if I think about the energy dissipation rate, so epsilon is the energy rate. Where in here, remember, we're in steady state. So I'm stirring the box at the outside. Things are cascading to smaller scales and then getting dissipated. So all the energy that I dump in is all the energy that gets dissipated. Otherwise, energy would build up in the system. And turbulence figures out a way to dissipate things on the right size scale. So epsilon here is going to be the energy injection rate. But because we're in steady state, it's also equal to the dissipation rate. So epsilon means a couple things. it's also equal to the transfer rate from one scale to another. So from large scale to small scale, energy is getting transferred also at this same energy rate, epsilon. I want to leave this up. I super wish there was a board all the way back here. Right here. Can I use this one? There you go. Yeah. Pascal's triangle. So, how does the energy get smaller? So, the energy dissipation rate in the inertial range is going to be, this is going to be a function of size scale L. I was using wave number before. We'll switch between the two. So, epsilon, it's a constant, but it's a function of L. Okay, so the L disappears. But this is the energy at a size L divided by the time to get divided by the time it takes to get the energy out of that scale. So I have this cascade. Let's draw it in L. So we start off at large scale, and the energy cascades down to small scale until we get to the dissipation length. So we have the energy at this part. How long does it take for it to shred to a smaller scale? Here's another question. What size scale does it shred to? Okay, this is a deep rabbit hole. We assume, and it's probably backed up, that the transfer is local in spectral space, so that you have a thing of a certain size, you turn it into a thing that's slightly smaller, not way fucking smaller. So the transfer is local in K space. So you go from one size to a slightly smaller size. How long does it take? So what's the energy at a scale L? That's just going to be v squared of L. So now my velocity is going to be a function of the size of the volume that I'm thinking about. So v squared is the energy, right? Where'd the mass go? We're incompressible, so I'm just going to set the mass to 1, because it doesn't matter what the mass is, because the mass is constant. So v squared is the energy. And the time, how long does it take to turn a blob of something into a smaller blob of something? It's about the eddy turnover time. What does that mean? That means just the time it takes for a thing to swirl around once. And this is equal to the size of the thing, L, divided by the velocity. So, the energy transfer rate in the inertial range goes like v cubed over the size L. And this is a constant. So, the velocity at a size L is equal to epsilon to the 1/3, L to the 1/3 times some number c. This is major result 1. I waved my hands like crazy to get this. Turns out it works out really well. There isn't a better derivation. There are different derivations that are also gnarly, and you have to wave your hands like crazy somewhere in there. Turns out this waving hands like crazy works great. So I take the Fourier transform of this. If I want to get the energy as a function of wave number, you have gathered by now that I like working in Fourier space. I like Fourier transforms, and I like working in wave number space because you get different information. So the energy as a function of wave number space is going to go proportional to k to the -5/3. So you invert this, square it, you get a 1 from the Fourier transform. You get E goes like k to the -5/3. All right. So that is the cascade. Is there anything else that I needed to say about the cascade before I go on? I don't think so. Does this make sense to everybody for the most part? there'll be a homework on this, so you'll have some time to play with these ideas. So that was Thursday's lecture in 2 minutes. So now I want to talk about new stuff. Correlation functions. So this is random. This is a random process. So I can't talk about what the velocity of x, y, z, and t. I can't talk about this. I can't write a function down that tells me this. It's fundamentally impossible. I think that it's probably actually impossible. I think that it's, but nobody's been able to do it yet. So I think it's truly chaotic and truly random. So we can't talk about that. We have to talk about averages. We're going to talk about averages of the velocity, or the velocity squared. Or I could talk about the velocity cubed. Now, and with each one of these, I learned something new. So from the average velocity, I get where the thing is going on general. And from v squared, I get what a typical velocity size is. And from v cubed, I get a little bit more information about how the velocity is distributed. If I take all of the moments, v to the n, if I have all of these for n goes up to infinity, that completely characterizes the function as well. That's kind of cool, but you have to get infinite moments. And when I try to do this, if I try to take this moment, so when I take this moment, this one shows up. So I can't ever get the average because the second moment shows up. If I try to make an equation for the second moment, the third moment shows up in the second moment.
Sounds like an increase in momentum.
It's an increase in complexity.
It's more about the time, but yes.
Yeah, all right. So anyway, so you get these correlation functions, they come out. So just talking about the moments is going to be useful, but also not all the story. So this is what a function is squared at one point, but what if I have the velocity at one point times the velocity at a second point? This just tells me more information. This tells me about, so I've got a point here, and I got a point here. This tells me about, if I have a velocity here, what's the likelihood that I'm going to have a similar velocity over here? So that's what this tells us. So I'm going to spend a minute and talk about, let's not talk about these guys yet. Let's talk about, this is a vector quantity, and that's horrid. Let's talk about, let's call it time. Doesn't matter if I call this time or space, but you see this shows up a lot in digital signal processing. So if you ever get into horsing around with digital signal processing, time series of things show up a lot. So if I have, say, density as a function of time, this could be a random chaotic function, but we want to talk about both the structure, about the structure in time. So if I have a fluctuation at one point, what's the probability of having a fluctuation at a little bit later point? Now, that could be 0. It could be 1. Depends on the structure. So let's, I cooked up a couple of examples. So here, why are you on the other side? Okay, so this plot, if these don't show up online, somebody remind me and I'll put them up there. I just cooked up these plots about half an hour ago. So what is this? So on the left is a random signal with some number of points. It has some randomness to it. This signal is highly correlated with itself. The correlation for this signal is 99%. So the histogram of the values is the next plot. So you can see that that ranges from, it's supposed to range from -1 to 1, but this is a small number of a random sample of stuff. So it didn't go all the way to -1, and it went a little bit higher than 1. And you can see the correlation function right there. So the correlation function, the autocorrelation function, let's see, you can call it R. Let's keep calling it R. R of tau, which is called the lag, is equal to the average of rho at t times rho at t plus tau. This is the same correlation function that he talks about in the book. I'm just doing it in 1D for a scalar quantity. So now we've got a time series, but I could make this a spatial correlation. That's just fine. So what does this mean? So this means that, so the angle brackets means average. So that just means integrate. This is my signal. This is my signal shifted by an amount. And we average with respect to time. So that means that I've got my signal, and then I take another copy of my signal, shifted by a little bit, I multiply them together, and I integrate. And that gives me this quantity. That gives me the second quantity here. Or the last quantity here. So you can see that in the horizontal axis, that's the lag. I called it N, I should have called it lag. You can see at 0 lag, the correlation is 1. That means that the two signals are perfectly correlated. That means if I have a value for that signal, I know exactly what the other signal is. The other signal is at 0 lag, so you know what it is because it's itself. It's a tautology. So anything at 0 lag is going to be 1. But at bigger lag, it's going to fall off. So this one falls off pretty slowly, so that you're at, when you've shifted the signal by like half the length, you're about 25% correlated. Maybe that's 40% correlated. So, and you can see that by looking at the plot. You know, if you're at one spot, you know what the points are nearby. Now, if we have a less highly correlated plot, this is a less highly correlated signal. This is only correlated to 30%, so that means that the integral of this is going to be 0.3 instead of 1. And you can see that it changes with space. This one now falls down really fast and then has a little bit of correlation at this. This actually looks like a random point, but it's not. I'll show you that in a second. So here's a less correlated spatial signal. It still falls in the same kind of range between -1 and 1, -2 and 2. But it's more correlated. This is what it looks like if you have more data. So here is an uncorrelated, oh, I should make it do that. Here's an uncorrelated data with better statistics. So now I've got 10,000 points, and you can see that it's correlated at 0 lag and at 1. So if I shift it by itself, it's sort of correlated. If I don't shift it at all, it's very correlated. Anywhere in the middle in this particular signal is not correlated. That's how I built this signal, is it's only correlated in one spot. And you can see from the signal itself that that's not correlated. There's no structure in there. But if I look at a more highly correlated, this is again a bunch more points. This is what I had to make a lot of 9s here. This is very highly correlated, very high sampling rate signal, and you can see that the correlation function again falls off instead of just being steep, because this is a more correlated signal. So correlation function tells me how big the structures are. It tells me if I've got some swirling, how much swirling is happening nearby. That's the technical term. Does that make sense? Everybody comfortable with this autocorrelation function?
Could you repeat what you just said about the correlation?
Yeah.
function?
So if my correlation function is, so my correlation function R versus the lag, let's say it looks like this, randomly. That means that if I have a random signal and I'm near it but not too near it, then I know that since the correlation is high, I know that the probability of this second point being similar to the first point is high. But as I get further out, the probability of this point being similar to this point is much lower because there's a lot more fluctuation that can happen. And the correlation function tells you how far, in this particular time in time, this tells you how far in time you can expect to see something similar to what you have at a given point in time. So, this is for a scalar. Let's do it again for a vector. And it gets hairier now because it's a vector. But really all we're doing, all of this exercise is just an exercise in boiling it down to a one-dimensional thing that we can deal with a little bit better. Come on. So the correlation function Rij at a separation r is equal to Vi at a position x, Vj at a position x plus r, and we average this over x. So to actually compute this quantity, what you do is you pick a point, you take all of the points that are r away, and you add them up. And then you do that for every other point. So this is a horrible function because it's got a lot of free parameters in it. It's got I and j, which are both indices, so this thing's a tensor, that's horrible. And we've got this r, which is now a free index. So this quantity has just as much information as v does. So that's problematic. But we can assume a bunch of things. So we have all these assumptions. We have homogeneous, isotropic, and incompressible, which all make things easier. So let's employ these, and let's talk about how turbulence should be correlated in space if we're away from the wall. So this homogeneous and isotropic and incompressible are all reasonable assumptions as long as you're not like near a wall or near the initial conditions or whatever. So as long as you're not near the boundary, this works pretty well. So if you've got like a boat and it's going through the water, it kicks up a bunch of wake turbulence. Near the edge of the wake, this doesn't work really well, but in the middle, it's pretty great. So what can I say about this? And what actually are we doing? So I've got a point in space here and a point in space here. And here, I nicely wrote down what I intended to say for myself. Right here. Okay, so let's talk about isotropy first. So isotropy says that Rij of R, this is a vector. So that is this direction, or this direction, or this direction, or this direction. It has magnitude and direction. But because it's isotropic, there can't be something statistically different in that direction than in this direction. So Rij can't depend on the vector r, it can only depend on the magnitude of r. How far away are you from a certain point? So this is Rij of the magnitude of r. Also, because it's isotropic, it doesn't matter what I call x and y, so I can change the labels on x and y all willy-nilly. So I can change I and j, so this is equal to ji. It's symmetric in that first quantity. So that's useful. So we've taken something that was a tensor with a vector argument, and now it's just a tensor with a scalar argument, so that's better. Much easier thing to deal with. I can plot this. It's hard to plot something with vector dependence. We can simplify this further by using the fact that it's incompressible. Incompressible gets you so many useful things in the world. It's a drag when it goes away. Incompressible means that drij, drj, now this r is this r, rij doesn't depend on x, it only depends on r. So I can't take a derivative with respect to x, it's 0. There's an x on this side, we integrate over that x though, not a free parameter. drij, this is equal to the average. Oh, also, I use angle brackets to denote average. The book uses an overbar. Doesn't matter. They're, as far as I'm concerned, they're equivalent. Generally, this means space averaging and this means time averaging, but since we're really doing ensemble averaging for everywhere, it doesn't really matter. But the angle brackets are a little bit more explicit, so I use those. So this is equal to drij, drj doesn't have any dependence on this, so this is the only thing we have to differentiate, so this is just equal to vi at x, dvj at x plus r, drj, this term is 0, so the whole thing is 0. Okay, if the derivative of a function is 0, with derivative of a function with respect to some variable is 0, what can you say about that function? It is linear in that function, in that variable, right? So this is at best linear, right? It can't be any higher than that, or all of my derivatives would be something goofy, and it wouldn't get up to, it wouldn't, the bits wouldn't cancel out. So it's got to be at best linear in Rij. So, okay, let's try to write something down. Rij, the lag, has got to be linear in Rj. So that's going to be m times Rj plus b. Everybody should hate what I just wrote down, because I have a tensor, a vector, and a scalar, and with the current algebra that we are dealing with, that is not possible. There are algebras where you can add a scalar to a vector and you get interesting things, and that's fun and fascinating, but we're not getting into geometric algebra yet. This one is not possible. So, okay, let's make this more general. Okay, I can make this a little bit more general too, because it can be linear in both quantities. And so this is m, ri, rj. Okay, that's A, more general, and B makes sense. Now it's a tensor. And B, that's got to be my constant. Now it's a tensor. Still not general enough, but it does make sense now. Oh, there's another thing that I could write down. I could write down epsilon ijk times rk. Now I've written down something that's a little bit more general. So here is 2 r's, here are no r's, here's 1 r. I've made it so that they're all tensors. That's what this epsilon ijk. Now this guy's a tensor. It's the only way to take a vector and cram it into a tensor that makes sense is contracting with the triply antisymmetric tensor. This guy has all of the isotropy properties that we need. So this isn't still general enough because it's linear in Ri and Rj, but in R, I don't have any constraints. So we can remake this as a function A of R times Ri Rj plus B of R delta Ij. And this last one we're going to throw out because it's antisymmetric. Epsilon ijk is the antisymmetric tensor. And I don't want antisymmetric, I want isotropy. I want my universe to be symmetric. So we'll just throw this one out because it violates our isotropy. So the correlation function Yeah, so our correlation function, the most general way to write it is going to be some function a of r, which doesn't violate isotropy, doesn't violate homogeneity, it's just a function of r, times ri rj plus v of r delta ij. Still ugly, I still don't have any intuition for this. So let's be a little bit more explicit, because this is still a gnarly tensor. And that's too many things for me to think about. I can think about like one thing at a time, maybe two things at a time. But this is 9 things at a time. So, okay, let's stop there. What is I, j, k? What is I? I is going to be x, y, z, right? Or r theta phi. It's fine. Or any 3 axes that I like. So instead of x, y, z, I'm going to say, here's point 1, here's point 2, here's the vector r that connects the two. I can think about this as, in this coordinate system, where one axis is along r, one axis is perpendicular to r, and the third axis is also perpendicular to r. So we'll call this, instead of x, y, z, we'll call this L, N1, N2. So L is along the longitudinal direction, along the separation. N1 is one perpendicular, and N2 is the other perpendicular. You got some freedom with how to choose those. They rotate, but it doesn't matter. So we'll only deal with one of those at a time. So RLN, so this means I want the correlation between 2 points, between the velocity, one velocity pointing at the other point and the other velocity tangential. So the correlation between, here's point 1, this is V1, and here's point 2, this is V2. And then R is the vector joining it. All of these correlations are 0. Because if I rotate this, I get that. But if I flip it, I get that. Oh no, if I flip it, I get that. And since it needs to be symmetric in reflection, that means that if I reflect it in space, I should get the same thing if I don't reflect it in space. But this is clearly the opposite. So this says the opposite sign of this, because this velocity is negative, right? I've just flipped space, so I just flipped this velocity. So all quantities that look like r times 2 orthogonal quantities, these are all 0 by the symmetry. Because you can just turn around and you should be able to see the same thing. But you don't, so it's all got to be 0. So all of the transverse components are 0. So this is the correlation of things going in this direction and things going in this direction. Those are all 0. Let's think about just the longitudinal and the longitudinal. So here's point A, here's point B, here's V1, here's V2. V1 and V2 are collinear. Then R, longitudinal, longitudinal, is equal to A of R times R squared, because that's all the difference, plus B of R delta ij. This is not summed over. This is, I'm just writing down this component. I'm not summing over anybody. Well, that's a little simpler. R normal normal, what's that equal to? Well, okay, so if I, here's point 1, here's point 2, here's V1, here's V2. So we still left with A of R, And then we got Rn, Rn. But how big is R normal? That is the amount of displacement perpendicular to the line. There isn't any. If I want to know how far down the line I went in this direction, that's 0. So this term is 0. Both of these separations, both of these lags are 0 because they're in line with each other. Does that make sense? Let me rotate it. Let's deal with one particular coordinate system. Now, R, my separation variable, is an x hat. So here's A, here's B, this is x. So the coordinates of this is x1, y equals 0, z equals 0. I can just translate so that that's true. This one is x2, y equals 0, z equals 0. So the difference in y here is 0. So our y is 0. So these two go away. And we're just left with b and delta on j. All right. One of the other things that we know is that at 0 lag, r at 0 has got to equal 1/3 v squared average. Why? We just look at the definition of it. Oh, I left the definition off. R, I, J, and R equals the average of V, I, and X. Vj of X equals R. So RII is just going to be one of these components. It's going to be 1/3 of V squared. So at 0 lag, we get 1/3 V squared for our correlation function. So we're just going to call RLL of R. We'll call this A of R, RLL. We're going to call this 1/3 V squared F of R. And RNN is just, again, 1/3 V squared G of R, where I've introduced this function f and g. Now, I haven't really done very much because I had a function that I didn't know how to deal with. But this is a horrible function that's tensors and takes a vector argument and is really too hard to plot. Yeah.
How did you convert the RL
To this, here I'm defining f this way. So at r equals 0, I have to get 1/3 v squared. That comes out of the math. And then above that, it's just some function of r. And it's going to look like this. So in general, I left a step out of my notes. Jerk. So the most general thing you can say is, sorry, that should be any. I'm going to write it better here. Rij is going to be, RLL is going to be A R R squared plus BR delta LL. No, that's, the delta goes away because L and L are the same. Equals 1/3 V squared F of R. And R and N equals V of R equals some other function G. And you can do a little bit of algebra, which isn't very hard. You just solve for A and B. You already know what B is, so you just get A. And you're left with the most general form that you can write. Rij equals 1/3 V squared bar. This is the most important bit. This is the RMS velocity of the turbulence. So this is how much energy is in the whole system. Times F minus G over R squared times Ri Rj plus G of R delta Ij. And I know because of the incompressibility condition that the derivative of this thing is 0. So the derivative of this thing is 0 gives me another equation to solve for G, and I can get that G equals f of R plus 1 half R df dr. Okay, great. So now I only need to find one function, f, instead of this nasty tensor thing. So unfortunately now we run into a wall of, well, we can justify making it simpler. That gets us something that's simpler. It's not a tensor anymore. It doesn't take a vector argument anymore, but we still don't understand it very well. That is the state of current turbulence research. We know, though, how it should look. We know that f of r is going to be 1 at 0 by construction. And we know that it's going to fall off and go to 0. So it's going to have some function like this. And one thing we can define is the correlation length, which is the integral of r divided by r at 0 lag. This just says make this a rectangle with the right area. How long is the rectangle? So I take all the correlation and make a rectangle out of it. That gives me my correlation length. So this defines the correlation length. So what sets the correlation length? We don't know. We don't have a good functional form for this. But it is set by the size of the turbulence. So turbulence that's more correlated will give you a longer correlation length. So what does this mean? This means that if you're in the ocean and you're bobbing up and down and your buddy's over there bobbing up and down, are you going to be bobbing up and down together? How far away does he have to be before you're bobbing completely out of phase and they're not related to each other? So the correlation length matters. Now, diffusion. So that is the correlation lengths. We're going to use these correlation lengths in a second by way of waving hands, because that's what we're doing today. So I'm going to go through turbulent diffusion first, because does anybody have, before I go on to diffusion, does anybody have any questions about these correlations? Yeah.
So you're saying that in order to describe the turbulence, we know there's some f of r, some function, right? But
Yeah.
we don't know specifically what it is?
Right.
Okay, cool.
Yeah. And it may change depending on the system in question. It may not be universal. It might be universal.
So
Hard to
people
say.
are working on that right now?
Not specifically trying to find this. They're doing other things. Like you can show that you can't write a function down for this, because if you could, that would solve the closure problem, which I'll talk about later next week. So yeah, kind of to answer your question was, are people looking for this? And no, they're using it. They're looking for slightly different things that I'll get into. Maybe I'll get into later. This is a tool for waving hands. Is there anything else I want to say? So most of the point of this exercise, like why did I go through all of this? I went from something horrible to something tractable. That's great. But also we talked about the symmetries of the problem. So there's rotational symmetry and translational symmetry. So even though it's chaotic and random, it's random everywhere, but there's still some correlation size scale. So you can still have structure even though it's totally random. So how do we use this, and what can we do for it? So I'm going to talk about the correlation length scale as if I know what it is, but we just have to approximate it. And I will approximate it in a minute, not today. But we'll talk about what the velocity does. So actually, I'll show you the more satisfying Richards diffusion first. So, okay. Well, no. Arguments with the squirrel brain. Squirrel brain says it wants to talk about the other stuff, but I'm not going to. Your position, the integral from 0 to t of your velocity. Now this is the Lagrangian velocity, not the Eulerian velocity that we're talking about. There's not really a difference, but we need to make that distinction because this thing is going to follow a world line, whereas a lot of times we're just talking about things stuck in space. And this is going to be 0. Oh, actually, this should be the average. I'll use an overroller for now. The average of x is going to be 0. Average of x squared is the integral from 0 to t dt prime, integral from 0 to t prime of v t d tau d b d prime d tau. Here's another v at one times v at another. This is another correlation function. I'm going to define another correlation function. Sorry for changing color midstream. R t. This is the time correlation. There's going to be a different function than the space correlation, but have the same basic properties. It's going to fall off of some time. It's going to look about the same. This, we're just going to define this as the integral from 0 to, boy, I got the drops today. 0 to t, how I want to define that? Just an average over t. It's triangle shaped, which is why it's impossible to hold. Which is a fascinating problem. So we get some correlation function as a function of time, so we can just rewrite this as x squared is equal to, here, let's call this so we see that at 0 lag, following what the book does to keep it consistent, but I kind of hate the way he did this. I've been teaching out of this book for a while now. I only hate it the way that he does this today. I didn't hate it last year, but I do now. So I had introduced these functions f and g, and then the correlation function is going to be v squared times f. I'm going to say we got some other correlation function r of t, and this is equal to v squared times some other function, but it's anyway, my notation gets a little mildly here. So r is 0 at 0 lag. So this is equal to then v squared r of t d tau. Tau in there. So, what does R of t look like? R of t looks like this. It's 1 at t equals 0. Or at delta t equals 0, and it falls off. So, if I'm way down here and I'm looking at very short time, so very short time or very small spatial separations, then this is basically 1. And my integral looks like basically v squared times the integral of 1 to t v squared t. So the average x squared is, oh, I'm sorry, I did that wrong. Let me do it all the way out and not skip steps. This is v squared times the integral of 0 to t dt prime, integral of 0 to tau, all right, 0 to t prime d tau of r. But if we're at short time or short space, then this is just equal to 1. So then I get an integral here that gives me a t, and I get another integral that gives me a t squared. So this goes like v squared t squared. So from a very short separation or very short time, x goes like t. X goes like vt. That's ballistic motion. That's what you do in 2048. Right? If we're much longer than that, these are the two cases that the book does, but not the interesting case. He skips the interesting case. If I'm much longer than need a different shot. That one's too droppy. Try this flat. Then we've got v squared 0 to t dt prime 0 to t prime d tau r t minus t prime. If t is now much larger than the correlation time, then this whole integral is equal to a constant. What do you call that? B? Because the integral r falls off after some time. So there's some correlation time, and r we can treat as 0 over that. So if I'm integrating way past this, then this whole integral is just a constant. And I'm left with x squared equals v squared times t. Just one t, not two t's. This is diffusive motion. Make sense? See how I got there? So, okay, in both cases, I've got x squared is equal to v squared, because this is just how I've defined my correlation function, so that it's v squared at 0 lag. 0 to t dt, 0 to t dt, r of t. I got sloppy. So if t is small, r equals 1, and x squared equals v squared t squared. If t is very large, then the integral from 0 to t of r is 1, or some constant. We'll put 1 in quotes there. Maybe it's a number, but it's a constant. And then x squared goes like v squared t. So if you're way below the inertial range, let's think about this inertial range that we do. You're way below the inertial range, in the dissipation range, then you just move around with the fluid. The fluid just pushes you around. If you're way above the inertial range, then it diffuses you. So what's it do in the inertial range? Oh, butts, I'm about to run out of battery. I hope I don't run out of battery before I stop talking, because I got 5 minutes, and this is the important bit. This is the bit that's not in the book, so let's all pray. I'll go fast. I'll go fast, so I'll make sure that I get it on tape. Okay, in the inertial range, V equals epsilon to the, we'll just call it epsilon. We'll just call it epsilon 1. V goes like L to the 1/3. V is dl dt goes up to the 1/3. I don't want L, I want L squared. I want the mean squared separation between 2 points. So I'll just dot this with L, and I'm left with 1/2. I'm going to throw this 1/2 away in a second just because I don't care about it. dl squared dt, I just multiply L, which is x squared, equals L to the 4/3. Okay, solve this. L comes over here, T goes over there. We get rid of the 1/2 because I don't care about it, because I'm waving my hands fast enough that you can't see a 1/2. So this comes over here, the T goes over here, and we've got L squared to the -2/3 dl squared equals dt. Okay, this comes over here and it becomes L to the -4/3, but the quantity that I'm integrating is L squared, because that's what I care about. So it's L squared to the -2/3. I integrate this and I get L squared to the -1/3 equals T. I integrate the other side and I'm left with L squared equals T cubed. This is super diffusive. This is faster than diffusive. This is faster than ballistic. So if you're way below the inertial range, it's ballistic. If you're way above the inertial range, it's slower than ballistic by a lot. If you're in the inertial range, it's faster than ballistic, because you have this V goes like L cubed that lets things carry you far away. This bit isn't in the book, so come back here. Yeah.
Is this supposed to be positive?
This is no, I just cubed both sides. Oh yes, that's a positive one. Yeah, sorry, because this goes up one by that side. So then L squared, you square both sides and you get L squared goes like T cubed. I'll just stop the recording so that it